So far, we have learned how to evaluate limits where a function is continuous and where the function has a possible jump or has a hole. In this section, we will be working with limits when our function has a vertical asymptote or end behavior. So these are limits that deal with infinity, the concept of infinity, and the actual limit value could be infinity. And with end behavior or potentially horizontal asymptotes, we know we are considering a limit as x approaches positive or negative infinity. So for vertical asymptotes, remember that there are four possible scenarios when we have a vertical asymptote. You could have an asymptote where our function is approaching the asymptote, approaching positive infinity on both sides of the asymptote, like it's going up, up. You could have a function where both sides, that looks a little funny, where both sides of the function are going down at the asymptote. You could have a function where one side we're going up from the left and down from the right, or we could be going down from the right and up on the left side of the asymptote. I said that backwards. Okay, so those are our four possible scenarios at a vertical asymptote. And really, in order for us to evaluate a limit at an asymptote, we need to know which one of those four scenarios it is. And so without a graph, we can do that with one-sided limits. So the first thing we're always going to do is check. So we're going to plug in our limit value. So I'm going to plug in 2. And I can see at the top I get 2 squared minus 3 times 2, so 6. And the denominator, I get 2 minus 2, which is 0. So we know that we have a vertical asymptote because when we plug in 2 to that limit, we get a non-zero number, 4 minus 6, so negative 2 over 0. All right, so that's the indication that we have a vertical asymptote. So now when we go to evaluate the limit, we have to evaluate the limit from the left and the right of 2. So I'm going to keep my limit notation here. All right, so the limit as x approaches 2 from the right of x squared minus 3x over x minus 2. All right, and well, we already plugged in the 2. So when we did that, we already have a negative 2 over 0. But what we need to imagine is that if we're coming from the left of 2 on the number line, we're approaching 2 from values that are really, really close to 2, like 1.99999, for example. So I need to think about the denominator, and I'm not changing anything about the numerator. I just want to consider what would the sign of the number in the denominator be. So if I subtracted 1.99999 minus 2, I'm going to have a negative in my denominator. So even though negative 0 isn't a thing, I can write this to indicate that I have a tiny, tiny negative number. So negative 2 divided by, again, negative 0. Well, a huge number like 2 or negative 2, well, it's not a huge number, but a number like 2 or negative 2, divided by a really, really small number, that's going to basically be infinity. And if you're not sure, you could check that in your calculator. Like if you just did 2 divided by 0.000001, because if you think about it, 0.000001 goes into the number 2 a lot of times. So when we divide by 0, even though we've, as math teachers, we tell you for years, you can't divide by 0. When we divide by 0, it's like we have that concept of infinity. So a negative divided by a negative yields a positive. So we would get a positive infinity for the left side, for this left-sided limit. All right, so then from the right, well, we said we plug this in. We already know the numerator is negative 2. Our denominator is now going to be, we're going to think of that as a positive 0. Because if I plug in a number that's just a little bit bigger than 2, like 2.00001, and I subtract 2 from that, I have a positive. So again, we got to follow those division rules. When I divide a negative by a positive, that's going to yield a negative infinity. So from the left of 2, our function is going up to infinity. From the right of 2, we're going down. And all we could conclude about this limit is that it's non-existent. So our limit as x approaches 2 of x squared minus 3x over x minus 2 is non-existent or does not exist. All right, our next example, we want to start the same way. So I want to plug in a 0 again, or plug in 0 because x is approaching 0. So 0 minus 3, we get a negative 3 on top. 0 squared is 0 on bottom. And again, it's getting a number over 0 that indicates that we have a vertical asymptote. So as we break this out into the two one-sided limits, we want to be careful with our limit notation. All right, so if I think about my numerator, as I approach 0 from the left, so a tiny negative number, when I square that negative number, I'm going to get a positive number. And for our limit as we approach 0 from the right, well, we're squaring a tiny positive number, so it's still a positive number. So both of these limits are a negative divided by a positive. So we are approaching negative infinity from both sides. So if we imagine what that looks like at our asymptote, the behavior of the function is going down, down at the asymptote. So we could still say this limit is non-existent. Technically, all vertical asymptotes, the limit is non-existent, but we want to be as specific as possible when we can. So we could also say this limit approaches negative infinity. All right, why don't you go ahead and pause the video, try that next example, and then go ahead and hit play when you're ready to resume. All right, so don't forget to plug in your 0. When we do, cosine of 0 over 0 is 1 over 0. So again, it's that number over 0, well, that non-zero number over 0 that indicates we have a vertical asymptote. When we check our behavior from the left, we get 1 over a tiny negative number. So that means we're going to negative infinity from the left, and from the right, positive infinity. So again, our asymptote behavior is going to look like that. Negative on the left, positive on the right. And so the best we could do is say that the limit as x approaches 0 of cosine of x over x is non-existent or does not exist. Okay, so that's vertical asymptotes. When we're talking about end behavior is more general. There's a lot of ways that we could consider end behavior. When we think about the end behavior of a function, we're looking at what's happening to our function at really, really, really big positive or negative values for x, right? So the end of a function is like way, way, way to the left and way, way, way to the right on our graph. So in short, when we think about end behavior, we're really just evaluating the limit of the function as x approaches positive and as x approaches negative infinity. So positive infinity being our end behavior on the right, negative infinity, our end behavior on the left. So another thing we might be asked to do is we might be asked to find the location of horizontal asymptotes. So that's a type of end behavior, but if you remember from Algebra 2, some functions have asymptotes. Some functions, like polynomial functions, go like up, up, or down, down forever. I'm thinking about x squared, negative x squared, or we could have a cubic function or really an odd function that has different end behavior where we're going up or down to positive or negative infinity forever. And then we also have functions like the sine function, and the sine function oscillates. So we know like the sine function's end behavior is not an asymptote, and it is not approaching infinity forever and ever. Rather, the sine function oscillates between negative and positive 1. Okay, so for this first example, when we are asked to evaluate the limit as x approaches infinity of e to the power of x, we want to be careful because sometimes The easy way to do this is by thinking of the graph or by just analyzing the function. So if I recall my graph of e, really all exponential functions of any base, as we approach infinity on the right, as x approaches infinity on the right, our graph goes up, up, up forever. It gets very steep. So from the thinking about the function in its graph, I know that my limit of e as x approaches infinity, my limit of e to the x is infinity. Now, you could also say that the limit does not exist because, again, the function's not approaching a particular value. Infinity is not a value. So we could think of it as non-existent. You could also think about this analytically. Like if you plugged in a really big number, like e to the, 100,000th power, can't tell you off the top of my head what that is, but that's a huge number. So as I continue to plug in larger and larger numbers, I know that e to the power is going to go to infinity. All right, so for the second example, we have to be really careful here because all of our exponential functions, their graphs are, they look different on one end than the other end. So going back to our graph of e to the power of x, we have a horizontal asymptote that we need to remember. So when we evaluate the limit as x approaches negative infinity of e to the x, this time our limit is 0 because our function going to the left does approach 0. It never reaches 0. So we want to be really careful there. And then similarly, like the one before, you could think about this analytically. Like if I plugged in a really big number for my exponent, a big negative number, let's say I plugged in like negative, 99,999. It's a pretty big number. I could think of that as being 1 over e to the 99,999 power. And you probably don't need a calculator to know that 1 divided by a really, 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 really big number is basically 0. Like if you brought one cookie to school to share with every single person in the building, no one gets anything. So we're dividing one thing by a huge thing. It's basically 0. All right, this last one, we also want to be careful about. I kind of hinted at this earlier. If we're evaluating the limit of one of our sinusoidal functions, such as sine or cosine, if we're looking at end behavior, something funny happens, and we're going to circle back to these functions at the end of this lesson. So if I think about the limit of sine of x, we said that the sine graph we know is going to oscillate between -1 and +1. And so at the ends, we don't achieve any limit since the function oscillates. So we could just say that the limit does not exist or is non-existent. All right, so at the top of page 8, we have other types of limits that are going to be more interesting and probably more challenging to think about when we have to evaluate them. And so, for example, you might notice that all of these expressions are like fractions. All of our functions have fractions in them. And we often have to think about how the numerator and the denominator are growing separately. So let's just look at this first example and then we'll come back and think about what's in the box. So if I plug in a really, really, really big number to this function, x squared plus 1 over 2x cubed minus x, if I plug in a big number and then I square it and then I add 1 to it, that's going to get huge. That's blowing up. So I could think of the numerator of this function approaching infinity. If I plug in a big, big, big number to my denominator and then I cube it, I multiply it by 2, and then I subtract a big, big number, well, that's still approaching infinity. And if you think about it, if you have a huge number cubed, let's say that you took the number 1 trillion, which has 12 zeros, and if you cube that, you're going to get a number that has 36 zeros. and then you subtract 1 trillion from that, again, that number has 12 zeros, you are going to still have a really huge number. So cubing a giant number and then subtracting that number from what you cubed, really the subtraction piece is insignificant. So when we look at this function, what we notice is that the top and the bottom are both just blowing up, getting really big. And really the only significant pieces in this expression, are going to be these fastest growing pieces. So in other words, we're going to think of these, the leading terms of the numerator and the denominator. We're going to consider our leading terms when we evaluate this limit. So if I consider the limit of, as x approaches infinity, of x squared over 2x cubed, well, now if I think about it, the bottom is growing a lot faster than the top. That's one way to think about it. So if I think of a fraction where the bottom is always getting bigger and bigger and bigger than the top, than the numerator, that's eventually going to approach 0. Another way of thinking about this is we could actually divide these fastest growing pieces. So we said this plus 1 and minus x are not significant. When we get here, we could actually divide the numerator and the denominator by x squared, and we would get 1 over 2x. So now if I plug in infinity to that, I get 1 over 2 times infinity, which is just 1 divided by a huge number. Again, infinity is not a number, and we would get 0. So as we're working through these problems, what we have to consider are different growth rates of different types of functions. That first one wasn't too much to consider because they're both polynomial functions. So in this box at the top, we're going to look at our growth rates from the slowest growing. So our logarithmic functions are the slowest to the fastest growing. And really for right now, at this part of the year, we're really only looking at these first 3 growth rates, and we will talk about the last 2 later in the year. The first one, though, is a logarithmic function, so a log function. So we know, for example, that the graph of the natural log of x, or any log really, of any base, it appears to become flat. It does not have a horizontal asymptote. It does continue to grow, but it's very, very flat. When we get to our next growth rate, we are now looking at polynomial functions. And so they could be a power function. They could be a polynomial function like 2x cubed minus x, like we just saw. And if I think about that, I could think of a linear function. Well, that's going to approach infinity, but it's, it's a line. I could think about the graph of x squared. So a quadratic function is going to be steeper. A cubic function is going to be even steeper. So the greater the exponent, so like I know x to the 4th power is going to grow faster than x to the 3rd power. We just have to consider, if our function is odd, are we going up or down at the ends? Well, I guess we also have to consider that if our function's even, if we have a negative out front. All right, so polynomial functions grow faster than logarithmic functions, but faster than that still are going to be our exponential functions. So we know exponential functions start off flat, but then they get really steep really fast. And again, this is end behavior. So we're not worried about what's happening at values of x close to 0. We're worried about what's happening to the function at huge values of x, close to positive or negative infinity. So just like polynomial functions, with end behavior functions, the greater the base, the faster the function grows. So e to the x grows faster than 2 to the x, but slower than 3 to the x, because e is about 2.7. So we know like 4 to the power of x would grow faster than 3 to the power of x. Okay, and we said these last 2 we're not really going to deal with right now. I don't know if you have seen this before, but this is what we call a factorial. So we will circle back to this later on, but a factorial function. And then I just want to point out that this last function is not a polynomial function. It's not an exponential function. It's x to the power of x. So I'm going to say not a polynomial function. So it is a variable to the power of a variable. And that is unlike anything else that we have talked about so far. So we won't need those for a while, but we will come back to that understanding. All right, so the first example that we worked already, we noted that the denominator of the function was growing faster than the numerator. So our numerator was growing slower. Our denominator was growing faster. And when that happens, we are going to approach 0, because eventually, when our numbers get really, really, really large, our denominator is going to be huge compared to our numerator, which is basically 0. All right, so for the next example, we want to think about the growth rates, but we have two different types of functions. The top x cubed, well, that's a polynomial function. The bottom e to the x, that's an exponential function. So as I'm thinking about that, I know that the bottom is going to grow faster because it's exponential than the top, which is a polynomial. And we're looking at this as x approaches positive infinity. So I should actually pause and say, be really careful with the exponentials. If we were considering the limit as x approached negative infinity, that was going to be something different entirely. So again, even though these are both blowing up, infinity cubed and e to the power of infinity, those are huge numbers. Because the denominator grows faster than the numerator, our limit is 0. And I shouldn't equate that to slower over faster. The limit as x approaches infinity of x cubed over e to the x is 0. All right, our next example might seem a little tricky. Now, if I, again, plug in infinity, or like mentally plug that in, because infinity is not a number, the square root of an infinitely large number is still going to be huge. And the natural log of an infinitely large number is still going to be huge. So when we compare the numerator and the denominator, we want to think about growth rates and recall that we could write the square root of x as x to the 1/2 power. So we are comparing, again, a polynomial function. I don't always think of x to the 1/2 power as a polynomial function. I think of it as a square root function, but it is a polynomial function. We're comparing that to a logarithmic function, and we know that logs are our slowest growing type of function. So at the ends, that is. So the denominator is growing slower than the numerator, which is growing faster. So when this happens, that means our numerator at the end is going to get really, really huge, and our denominator is going to be really small in comparison. So this means that we are approaching infinity. And again, we could also say that this limit is non-existent. So up here at the top, when we have a faster growing numerator and a slower growing denominator, that's going to be, depending on the sign, plus or minus infinity. And again, we could think of that as being non-existent. So that means that our function is going to continue to grow forever and ever. All right, these bottom 3 examples are a little more complex. And when we look at this first one, if I think about it, if I plug in infinity, they're both blowing up. They're both getting huge, both the numerator and the denominator. I don't need to worry about the other parts of the other terms in the numerator except for the leading term, because again, infinity squared is so much bigger than like 15 times infinity. Squaring a huge number makes it so much greater than that number itself that it doesn't matter if I subtract 213 from it. It doesn't matter if I add 15 times a huge number to it, because squaring the number by itself is so significant the rest of the values would be small in comparison. So it's kind of like if a really, really rich billionaire were to drop like, a $50 bill on the ground, like, would they even go back and get it? Is it even worth their time? Probably not. Like, they have so much money. $50 means nothing to them. Whereas $50 would personally mean a lot to me because my my wealth is so much less in comparison. We'll just say that about it. So as we look at this function, we really don't need to consider these more slow growing pieces of the numerator and the denominator. We really just want to look at our leading terms. And so we could just consider the limit as x approaches infinity of 3x squared over 2x squared. And these are both quadratic. They're both polynomial and they're both quadratic. So this is an example of when the numerator and the denominator are growing at the same rate. So we don't have one that's faster than the other. And so if I think about this, I could plug in infinity and see that this is blowing up on the top and the bottom, but I can also just divide those pieces and I end up getting my limit is 3/2. So our limit is 3/2. We can divide by our x squared. And what that indicates for us, even though the question was just to find the limit, to evaluate the limit, if I evaluate the limit at the end of the function and I get a value, that means that I have a horizontal asymptote on the right side of the function. So we do have a horizontal asymptote on the right side of our function there at 3/2. And going back to these first two limits that we evaluated, when we got a limit of 0, that also means that we have an asymptote at y equals 0 on the right side of the function. All right, this next limit, again, we want to look at the numerator and the denominator carefully. And what I notice in the numerator is that the term that's growing faster, 2e to the x, is not written first. Like, I might want to rewrite this as like -2, oops, I don't like how thick that is. I might want to rewrite this as -2e to the x plus 4. You don't have to. I'll just tell you, I personally would probably make a mistake if I didn't do that. I should probably keep my limit notation there. All right, so again, as we plug in positive infinity, the numerator and the denominator are going to blow up. Oops, I dropped my x there. So I have -2e to some huge number plus 4 times that huge number divided by 3e to some huge number. And again, it's this idea of growth rates that an exponential function is going to grow so much faster than a linear function at the ends of a graph for really, really large numbers that this 4x is super insignificant. So really, we want to consider the limit as x approaches infinity of -2e to the x over 3e to the x. And when we drop that plus 4x in the numerator, this makes it a lot more simple. And now we can also just divide by the e to the x pieces. So we're going to get that our limit is -2/3. And again, that is an indication that we have a horizontal asymptote. So notice that this was another example where the growth rate on the top and the bottom is the same. It's exponential on top, exponential on bottom. All right, this next example, we have to be really careful about. It seems maybe a little straightforward, or maybe it doesn't. So again, if I plug in infinity or a huge, huge, huge number, my numerator is going to blow up. That's going to get really, really big. My denominator is also going to blow up and get really, really big. And just like before, that 10 inside of the radicands, so we're looking at the square root of 9x squared plus 10 in our numerator. When I'm plugging in a huge, huge, huge number, adding 10 to it is going to be very insignificant. And also subtracting 2 from 4 times a huge number is insignificant. So really, we could consider the limit as x approaches infinity of the square root of 9x squared over 4x. But here's where we need to be really careful, and that is that the square root, I'm going to write this out to the side in no man's land, the square root of 9x squared is not 3x. So here's why we want to be careful about that. If I think about it, let's say that x equals 3. So if I think about the square root of x squared, the square root of 3 squared is the square root of 9, which is 3. But let's say that x equals -2. So again, if I'm plugging this in, I'm just considering the square root of x squared. Well, -2 squared is 4, and the square root of 4 is +2. Like, I don't see a negative sign out in front of my radical. So I have to be really careful. I cannot draw the conclusion that the square root of 9x squared is 3x. What I can draw, because depending on the sign of x, that could become a negative number. What we can think of, though, is that the square root of 9x squared is the absolute value of 3x. So going back to like this example where x was -2, the square root of x squared is the absolute value of x. So the square root of -2 squared is the absolute value of -2, which is 2. So in this particular problem, that's not going to be very significant because we're evaluating the limit as x approaches positive infinity. But in a moment, we'll just look at what would happen if we were approaching negative infinity instead. All right, so if we come back to our limit, we said we could think of this as the limit as x approaches infinity of the absolute value of 3x over 4x. And so again, when we plug in a huge, huge, huge positive number, we said that is blowing up. And so we're plugging in a positive number. The top is going to be a big positive number because it's the absolute value of 3 times a huge number. The bottom is also going to be a positive number. So we can still think of like dividing off those x's, and our limit is going to be +3/4. But I just want to point out how that could have been different. Let's say that we evaluated the limit as x approaches negative infinity of the square root of 9x squared over 4x. So again, we said this would be the same as approaching the limit as x approaches negative infinity of the absolute value of 3x over 4x. Well, now, if I think about this, my numerator is blowing up towards positive infinity because it's 3 times a huge negative number, but we're taking the absolute value. My denominator, on the other hand, is going to be negative. So we have to be really careful. We can still divide, but our numerator is going to be positive, our denominator negative. So we would get -3/4 for that limit. So that's just a small thing that we really need to look out for. All right, finally, if we're finding the equation of horizontal asymptotes, that is just another way of asking us to think about end behavior, because again, a horizontal asymptote is an end behavior. So anytime we're asked to find locations of or equations of horizontal asymptotes, we want to consider the limit of our function as x approaches positive infinity, that's our end behavior on the right, and the limit as x approaches negative infinity of our function. So if we evaluate the limit as x approaches positive infinity of 2e to the x plus 4 over 5e to the x minus 2, well, again, as I plug in an infinitely large number, the top is blowing up. That's getting huge because it's an exponential plus 4. The denominator is growing up, and that's getting huge. So if I just look at my fastest growing pieces, I could consider the limit as we approach infinity of 2e to the x over 5e to the x. And again, the reason that we can ditch the +4 and the -2 is because we're plugging in huge values, and 2e to the x is so big with a large number that adding 4 is insignificant. All right, so as we plug this in, we see the top and bottom are growing at the same rate. So we could just divide by those pieces, and we are left with 2/5. So we will have a horizontal asymptote at y equals 2/5. That would be our equation. All right, we also need to check our limit as we approach negative infinity, so the limit on the left. And we have to be really careful, we said, with exponential functions, because when I plug in negative infinity, this does not blow up. Remember, e to the x is approaching 0. So this is going to become 0 plus 4 in my numerator. And I can't ignore the 4 if I'm adding it to 0. That's very significant. Like if I have $0 and I find $4 on the ground, that's going to, change things around for me by about $4. As opposed to like if I have millions of dollars and I find $4 on the ground, I'm probably not going to pick them up. All right, and then in our denominator, we have 5 times 0 minus 2. So we end up thinking about this one a little bit differently, but we end up getting a limit value of -2, and we do have an asymptote at y equals -2.